This lesson deals with lab number 3, which is Wheatstone bridge applications. A Wheatstone bridge is an instrument that is used to measure an unknown resistance, and it does this by balancing two sides of a voltage divider. It was first invented in 1833 by Samuel Christie. It was really improved by Charles Wheatstone in 1843. Let's take a look at the configuration of a Wheatstone bridge. Suppose they have 5 resistors, so R1, R2, R3, R sub S, and R variable. Suppose that I vary this resistance such that the current in this resistor is equal to 0. Okay, what does that imply? Well, let's write down that this is equal to 0. That means that the current in R1 is the same as the current in R2. Now, if you recall from ECE 201, that was the condition that we needed for a voltage divider. In other words, the voltage across R2 is going to be equal to R2 divided by R1 plus R2 times the voltage across them, which is our function generator voltage. The same is true on this side, that this current would have to equal this current because the current coming in here is 0. And again, that would mean that the voltage across here would just be our voltage divider rule, which would be R variable over R sub S plus R variable times the voltage V sub Fg. Now further, if the current in this resistor is 0, then the voltage across it is also equal to 0, because the voltage is equal to the current times the resistance, but the current is equal to 0. Now what that implies is that this voltage equals this voltage. In other words, the rise in voltage would equal the drop of 0 plus this. We're going to use that to solve for what's called a balance condition on the next page. And so here's the voltage divider on the left-hand side equal to the voltage divider on the right-hand side when the current in the resistor R3 is equal to 0. What's interesting here is that the value of the function generator voltage drops out. So if this were a battery pack instead of a function generator, as the battery pack is aging, the results we're about to derive don't change. Let's do a little bit of algebra on this equation. Let's divide the numerator and denominator by R2. So I get a 1 in the numerator, and then I get R1 divided by R2, and then R2 divided by R2, which is equal to 1. Do the same thing on this side of the equation, divide by R variable. So you get a 1 here, divide this by R variable, and then likewise here, get a 1. That implies that this quantity is equal to this quantity. Let's write that down over here. Now, the balance condition is the following. If I were to cross multiply here, R1 times R variable is equal to R2 times R sub S. Now, you don't have to memorize this formula, but I like to know these things so that I can write them down quickly. And sometimes in lab, it helps me get through a problem quicker or a calculation quicker. Now, what is this? If you go back and look at the previous page, we have a balance condition when we vary this resistor such that this current is equal to 0, and that implies that R1 times R variable is equal to R sub S times R sub 2. Now we can solve that equation for R2 if R2 were an unknown resistor. So let's do that on the next page. So here's that balance condition. Now let's just solve for R2, which would be R1 times R variable divided by R sub S. So if we had measured the resistor R1, R sub S in advance, and R variable is actually going to be a collection of precision resistors configured with a switch, then if I pick R1 equal to R sub S, then R2 would just be equal to whatever R variable is. That would allow us to measure an unknown resistance by pre-measuring other resistors, and we could do that with a voltage source and an ammeter and figure out the exact values of resistors and then build an instrument. And in fact, that's what this was done as the first resistance measuring device. Here's a picture of a Wheatstone bridge, rather an old instrument. The way it's set up again is that R1 and R sub S are precision resistors set equal to each other, and R variable is a collection of precision resistors on parts of a switch, and when you rotate these switches, you actually get the value of the unknown resistance. And you vary the switches until the current in this meter goes to 0. This turns out to be a very, very precise technique if you had precision measurements on the resistors, so you can make it as precise as you wanted to. Although this is a very old idea, we still use this concept in many, many instruments. In fact, we're going to use this idea in our scope probes. Now, besides the resistive voltage divider, there's a thing called the capacitive voltage divider. It's the same idea. We'll put two elements in series. Now we'll put capacitors in series instead of resistors. And we're going to solve for the voltage across each capacitor. Now we'll be doing this in the frequency domain. So we've got a AC signal coming in here. So we've got a phasor voltage. And we're going to solve for the phasor voltages V1 and V2 across capacitors C1 and C2. Now because they share the same current, we can use the voltage divider rule. So it's going to be the impedance of this element divided by the impedance of the sum of the two times Vn for the voltage V1. Likewise, the voltage V2 is going to be the impedance of C2 over the sum of the two impedances times Vn. Multiply numerator and denominator by j omega C1 C2 over j omega C1 C2. In other words, multiplying by 1. Now the numerator, if we multiply this term out here, the j omega and C1 cancel, we're just left with C2. In the denominator, the j omega C1 cancels with this term, and we're just left with C2. And for this term, we're just left with C1. What we've got is that the voltage across the capacitor C1 is the other capacitor over the sum of the two times Vn. This is sort of like our conductance voltage divider of ECE201. This is happening because of the reciprocal relationships. The same thing is true about the voltage across C2. If you multiply through by this same 1, the j omega C2 cancels, you're just left with C1. J omega C1 cancels here, just left with C2. And then this other term here cancels with this, and we're just left with C1. So the voltage across C2 is the other capacitor over the sum of the two. Easy way to remember that, just like we are a resistive voltage divider. We don't have to rederive it each time. It's a handy little thing to keep in the back of your mind. Now let's take our resistive bridge and let's replace the resistors by some capacitors. What we're going to show on the next page is that we can actually solve for one of these capacitors by varying a resistor. Again, suppose I vary this resistor such that this current is equal to 0, and that implies that this current is equal to this current, and so we have the capacitive voltage divider on the left-hand side of the circuit. So that implies that this current is the same as this current. I got a resistive voltage divider. R variable over R variable plus R sub s times V, a function generator, is the voltage across this element. But with no current here, I have no voltage across here because 0 times R3 is just equal to 0. So this voltage is the same as this voltage. In other words, the rise in voltage equals the drops around the loop. Take a look at that equation and see if we can solve for the capacitor C2 on the next page. Setting the capacitive voltage divider equal to the resistive voltage divider, we again have the function generator dropping out, so it's independent of that. And then if I divide on the left-hand side of the equation by C1, I get a 1. In the denominator, a 1, and then C2 divided by C1. On the right-hand side of the equation, let's divide by R variable. Get a 1 in the numerator, R sub s divided by R variable, and then plus 1. And that implies then that this quantity is equal to this quantity. C2 over C1 is equal to R sub s over R variable. Now let's cross multiply. C1 times R sub s would then equal C2 times R variable. And this is our new balance condition. In our previous case, we had the cross arms multiplying, but because of the impedance of 1 over SC, we have the two top elements multiplied together equal to the two bottom elements multiplied together. And now we can solve for C2. It's going to be equal to R sub s C1 divided by R variable. I forgot to mention in the last derivation, the resistor R3 was representing a meter, and this result, like that one, is independent of R3. So whether we have an ideal or non-ideal meter, we still get the same balance condition in our Wheatstone bridge and now this in our impedance bridge. Now this idea is used in the scope probe. Let's take a look at what we're going to use in lab. This is going to be an Agilent 173C 10-to-1 probe, shown here. And what's inside of it is the following. In the tip, there's a 20 picofarad capacitor in parallel with a 2 megohm resistor. Then there's a cable, which has about 10 picofarads per foot of capacitance. And then at this interface with the scope, and this large plastic connector, there's a variable capacitor, and you can see the little set screw that's here. We're going to vary that. And in parallel with that is a 285.7K resistor, and then the scope itself. We're going to connect this to the B and C connector. And that looks like in 1 megohm and 8 picofarads in parallel, as we had mentioned in the previous lab. Let's take a look at redrawing this picture on the next page. The probe tip had a resistor of 2 megohms. I'll call that R sub A. In parallel with that was a 20 picofarad capacitor. I'll call that C sub A. And then we had the interfacing of the scope and the end of the probe, which had a 285.7K resistor, and the scope looked like 1 megohm. Those two in parallel are 222.2K. And then I had the capacitance of the cable, which is about 10 picofarads per foot, the 8 picofarads of the scope itself, and then a variable capacitor. These are just a series of metal fins interwoven, so as you turn the set screw, we can change the effective capacitance. So our total capacitance, I'll call that C sub B, is going to be whatever the cable turns out to be, wherever we set the variable capacitance plus the 8 picofarads of the scope. Let's redraw this one more time, where I have R sub A and R sub B, that's right over here. Then I've got C sub A and C sub B right over here. I've got a short between the two. Here I've got my Wheatstone bridge kind of configuration, and if I pick the balance condition, in other words, the product of the two top elements equals the product of the two bottom elements, then the current in the short circuit is equal to 0. What that implies then is that C sub B is equal to R sub A times C sub A divided by R sub B, that's shown over here. R sub A was 2 megohms, C sub A was 20 picofarads, and R sub B was 222.2K. That gives me a value C sub B needing to be equal to 180 picofarads. So we can obtain that with results we have here. The cable would be 3 feet, 30 picofarads, and so we can subtract that off of the total we need to have, and we can adjust that variable capacitor. Now, when you do have the balance condition, again, the current in the short circuit is 0. You could remove the short circuit, and what you've got is a capacitive voltage divider and a resistive voltage divider. Okay, the resistive voltage divider is going to be V out, what we're trying to measure, times RB over RA plus RB. And we're setting this up to be equal to 1/10, with the value of R sub B being 222.2 K. And R sub A added is just 2 megohms added to that, so we get a value of 1/10. That's also equal to the capacitive voltage divider of C sub A over C sub A plus C sub B, and that's also set up to be equal to 1/10. To get that balance condition, we actually have 1/10 the signal shown on the face of the oscilloscope. Now the scope senses the connector and actually adjusts the scales for us so that we don't have to multiply results by 10 to get the actual value. With the short circuit removed, we have a series combination of C sub A and C sub B, and that would just be equal to the product over the sum. So it'd be C sub A being 20 picofarads, and C sub B we're setting equal to as a total of 180 picofarads. So we have an equivalent capacitance of 18 picofarads. Then we also have a series combination of R sub A and R sub B, and that's going to be 2 megohms added to 222K. So this is effectively our load seen by our circuit when we connect the oscilloscope probe.